let's, that's the control potential simulation. Again, as I said, it's on the web page, so if you want to, I would recommend you download it and you can play around with it and see how it's actually put together, and you can compare the book, program in the book to the spreadsheet, and if you've got some experience in spreadsheet, you should be able to figure it out. If you've got some experience in Fortran, you should be able to figure it out from that way. So let's figure the spreadsheet out. So it's a pretty good little program, but it's pretty basic. You know, it's not going to solve any of the world's problems, but it gives you an idea how you'd go about setting up a simulation like that. Let's take a look at what happens if we get into more interesting processes. Control equation, not really that interesting to simulate since we have an analytical solution to it. What happens though when we have reactions like this, where we have, in addition to our normal electrochemical process, we have a reaction in which the chemical undergoes some sort of chemical reactions, perhaps decomposes to species B, or a species C, I should say, and that species C may or may not be electroactive. Let's assume it's not electroactive. And so what's going to happen, you can think about what's going to happen. As soon as we start making B, it gets chewed up by the chemical reaction to form C. And depending on the rate constant, if it's a very large rate constant, that reaction will be very rapid. If it's a small rate constant, it's going to be less rapid. This would be a good example of a problem that we'd want to simulate because the chemical or the analytical solutions may be difficult to characterize. And one way to go about this is to set up our calculation for B just like before, and we would have the fraction of B in some particular box, some particular time, and then we would say that would be equal to two parts. A part that we'll call F prime B, and a part that would be a function of the discretized chemical reaction. What we're doing here is doing a serial process. We're letting the diffusion occur, and that's what we're going to call F prime B, is only diffusion occurring. And then letting our chemical reaction occur on this diffusion process on top of that. So we get overall the final result F sub B, but it's a function of two steps. One, we let the diffusion occur, and then we let the chemical reaction occur. So the advantage of this is that we have two separate steps, and we don't have to put them together into one chemical equation or one equation. A chemical reaction, say for a first order reaction, would be like so. We have a KT would be the typical non-discrete reaction would be going on. So we can multiply K delta T times the concentration of B in a particular time and space, or discrete form would be K. Now K is not the K, that's unfortunate terminology here. The K is the rate constant here. Let's make that a different color so we know what the difference is. That's the rate constant K, not the index in our time K. All right. So in this K is the time index K. All right. So that would be an example. We would have a reaction occurring. Now we have to somehow make that into a dimensionless form, and that should be fairly straightforward once you start thinking about this. Now this is sometimes a tricky process because what we're doing here is making two separate processes occurring at the same time. Diffusion occurs at a certain rate and would depend on the rate or diffusion coefficient. Rate constants occur either very rapidly or very slowly, and what can happen, particularly for chemical reactions, is I can have a chemical reaction in which the rate is so fast that B can never really get a chance to diffuse anywhere. It occurs, all the chemical reaction would occur in the first box. Well, in that case, our model would not very accurately capture the effect. And what we want to do is make sure that if our model is occurring to accurately capture it, we want to have that time such that the chemical reaction occurs over a number of boxes rather than just the first box. So particularly if the rate constant of a chemical reaction is very fast, you get into situations they call them stiff problems. They have to make a very large number of time iterations or chop time up into very, very short increments to accurately capture a very fast chemical reaction and simultaneously a slower diffusion process. So to accurately model both together can sometimes be tricky. And so that's where a lot of work goes on. That's especially where these efficient algorithms are good at, is calculating these sorts of things and avoiding that problem. The calculation we've talked about now really is not very good at handling fast chemical reactions. Let's think about another couple of problems, and we'll hang this set up for a while. What about reversible systems? We've talked about the Cottrell case, where A is a reaction that can go to B. Now, when we're talking about reversible, we're just talking about situations where we have a Nernstian concentration gradient profiles at the electrode surface. So the potential would be equal to the standard potential plus the natural log of the concentration of A at the electrode surface, concentration of B at the electrode surface. Or in a discrete form, we would write E norm, which is our dimensionless potential, and you see multiplying the potential times NF over RT is removing any voltage out of it, so that's a volts times reciprocal volts. And so that's going to be equal to the natural log of these two fractions of A and B at the electrode surface. And so the surface ratio of A and B is now not 0 as we had in the Cottrell equation, but it would be set by the Nernst equation. So whatever potential we're applying, we would normalize it and then calculate the ratio of A and B we require at the electrode surface, and then set in our model those to be the case. So we would just calculate via the model the concentrations of A and B. So rather than 0, it would be whatever they would be here. Now the current that we would see would be whatever current would be required to convert the material to set the proper concentrations of A and B. So there'd be some coming in from diffusion, but then we would also require some electrolysis to set the proper concentration. So we'd let electrolysis occur into that box and then say, okay, what amount of chemical reaction do we need to get A and B to the proper ratios? And that would be how much current would flow, is how much electrolysis we're doing. Now for heterogeneous kinetics, we'd do a similar situation, except that now the concentration of the A and B would not be set simply by the potential, but would also have to include the standard rate constant. And I have equations for that in there. I'm not going to write it down. But you could imagine that the similar process would now be occurring. We would set, instead of just by the potential, we'd set it including additional rate constant effects. And this would be for potential steps. It also could occur, we could also do the same basic process for potential sweeps, topic we're just going to talk about just in a second. In this case, the potential is not a constant where it is here and before, but it's going to vary. And usually we're talking about linear potential sweeps, so in that case the E would be whatever the initial potential would be. So we're talking about a potential sweep with the E initial, and then there would be a sweep rate times time to give us the increment in potential with time. So at some point time along down the road, we would have some potential that would be different from the initial by the factor Vt. And so our normalized potential would be similar to before, except now we have to include our Vt term in there. So here's our before, here's our VT term basically in there. And so EI norm would be dimensionless initial potential, and then we have a term that would be our dimensionless variable potential, and our units would be something like so, where we have, again, this NF over RT is allowing us to cancel out the voltage part. This would be canceling out the time part. In this case, a characteristic time rather than the step time or of the sweep, we don't have a step time anymore. So what we can use for characteristic time would be a convenient unit, for example, one that gets rid of this NFV over RT. And so in fact, we'll set T sub k for our characteristic time in cyclical in linear sweep situations would be RT over NFV. And so E norm in the sweep calculations would be the initial normalized potential plus this K over L, where K now over L would be the increment in potential as we go along. So that would be easy enough. We would just, at every time we have a new K, we would just add a little bit of increment onto the normalized potential. And we'll actually see that. We'll have some calculations where we show, with digital simulation, we'll show you how you do that calculation with incrementing the potential like so. Okay. How are we doing here? All right. Now we'll return a little bit to these digital simulations after we've discussed briefly potential sweep methods. Just a note for you guys. One, if you look in the syllabus, you'll see that after Chapter 6, we're going to skip ahead to Chapter 12, and then we'll go back to pick up some other chapters. So we're skipping ahead to Chapter 12 after Chapter 6. So after we're going to go through this chapter fairly quickly. We'll be done with it next time. Then we'll start doing Chapter 12.